So there are two types of circuits,
Okay.
series and parallel, and there are advantages and disadvantages to each. A series circuit has one path, and a parallel circuit has more than one path. We're going to follow a couple of other fundamental rules when analyzing these circuits. There's the loop rule, this is a review. The loop rule says you must, and I'm going to use the correct electrical engineering term, you must drop all voltage. Yeah, I doubt that very many engineers say drop it like it's hot when they're analyzing circuit diagrams, but maybe there's one or two out there.
When the circuit gets really hot, they're probably going to drop it. And the instructor's going to be like, drop it when it's hot.
Well, that's a difference. Yeah, drop it when it's hot.
Versus drop it like it's hot. I don't remember any of my physics professors.
Liddell says that we're talking about cosine.
Yeah.
She says drop it like it's hot when you talk about cosine?
Yeah, when you draw the little graph thing, you have to drop the line down to make the
Oh,
triangle.
so, she is so street, isn't she? Mrs. Waddell.
I don't even remember what that was for, I just remember that happening.
For like graphs, I was just talking about,
Mrs. Waddell watches, really inappropriate comedian. Really, really inappropriate. Can't think of it. Yeah. She likes Tosh. Ask her about Tosh sometime. It's like her guilty pleasure.
Can I have a credit phone for that?
Maybe.
People the internet?
I love Mrs. Waddell. She and I are Thelma and Louise.
Wait, what?
That's an old reference that you, did you? Over the cliff, baby. Me and Mrs. Waddell. All right.
And then they did survive that.
Hello. Well, yeah, there was that.
Yeah. I'm sorry, that's not the main point of the movie. It's about sisterhood and...
So those are the rules. Listen, guys, those are the rules that we're going to use. And we're going to use that along with Ohm's law. Okay? So one path, more than one path, must drop all the voltage available in a loop, and then the junction rule, which you practiced last night, current in equals current out. We're going to start with a series circuit. And a series circuit is one path, so I'm going to start drawing the schematics. I love drawing schematic diagrams.
Those Christmas tree lights?
Sure. They're Christmas tree lights. One path, we're going to have a 6-volt battery, and these are all 2-ohm resistors, okay? Yep, upside down horseshoe. So this is just like Christmas tree lights, 3 light bulbs in a series. When we analyze this, we're going to analyze both the current and the voltage. So there is a relationship to figure out the total resistance. So as if you could boil this down to one single resistor. And this you might have learned in middle school. Yep, when they're in series, you just add them. Dot, dot, dot. As many as you want when they're in series. So what would, in this particular case, what would the total resistance be? 6. 2 plus 2 plus 2. Then we can proceed to use Ohm's law to solve for the current coming out of the battery. Ohm's law is V equals IR. Total voltage, 6-volt battery. Total resistance, 6 ohms. What's the current? Can you solve that? 1 amp. That's correct. So 1 amp is coming out of the battery. And since there is only a single pathway, that current has to be conserved. So that means 1 amp goes through this first resistor, this first light bulb. 1 amp through the second light bulb, and 1 amp right here. I know this seems painfully slow and easy, but trust me, I'm going to make it harder. Oh, because conventional current always leaves the cathode, the longer line. Yep, and it is backwards. Now I'm going to draw these little things that look like spiders, sort of. No, these are voltmeters. Sorry about that, Varun. So the spiders are voltmeters, and the reason I draw them outside is because it's just going to measure the voltage that's dropped across each of the resistors. The current, notice that's like the water in a hose, right? And that gets an arrow because that flows through the resistor. When we play with resistors and current and ammeters and voltmeters in the lab, they're going to work exactly like this. The ammeter will be put into the circuit. So you'll put like an ammeter in like as part of the circuit. And the voltmeters you'll just sort of clip around each of the resistors. It's like you're testing to see how much voltage is being dropped, or you can kind of think of it like sucked up or used at each appliance, okay? Now these are nice and evensy-stevensy, so I can evenly split the voltage. So if I have 3 even resistors, 3 goes into 6 how many times? 2. So we're going to use up 2 volts each, and then we're going to double check it. Shabert.
So for current,
Yes.
whether it is moving electrons or is it just a moving charge?
Current travels through the medium of that C of E, moving electrons, but technically it's not like electrons marching down a wire because that would take forever. So this is instantaneous. This happens at the speed of light,
Okay, so
or
it's
dang
like
close
in
to it.
chemistry that like current is the movement of positive charges.
It is, but that's conventional current, but it's backwards. That's because the first bald white guy who said, hey, let's make current flow, picked positive. You and I both know the positive charges, right, right. But we still follow that tradition, even though it's wrong. Yes?
Can you refresh my mind what an ohm is again?
Ohm is the unit for resistance. Tommy?
How do we know it's 1A?
From this right here, I equals 1 amp. Now, if I did a little mini Ohm's law equation at each resistor, it should also work. So this is like for the whole circuit, right? A 6-volt battery, a total of 6 ohms, so that means 1 amp gets pushed out of the battery. But if you look here, 2 volts, so V equals I times R, 2 equals 1 times 2. 2 equals 1 times 2. 2 equals 1 times 2. V equals IR should work at every spot. Okay? Now, if I were to take my little spider voltmeter thing and move it around, I want you to see if you can figure out what the voltmeter would read, what it would measure. So if I took this voltmeter and I went like this, right here, just on the wire, what's it going to read at this spot? No. No.
Zero.
It won't read anything. That is correct. Why?
Because there's no resistance.
Right, there's no drop. So a voltmeter measures how much voltage is used up. So there's still, what if I put it like here to here across the terminals of the battery?
0.
That'll actually read 6. The difference, the terminal voltage is the difference between the positive and negative terminal. That's correct.
So is it like when it gets after the second one, it only has like 2 volts left worth of energy, and
that's
so then
correct.
it has to like be recharged to do the loop again?
Yeah, that's a very good way to fix it. Arthur? Because this wire is very short and a very good conductor, and it basically has 0 resistance. Now, if I took this same wire and stretched it for miles, and then like did my volts drop, then it would show.
Talk about the end, the start and the end, why you can talk about that.
Is it the only way on the side?
I'm not sure I understand the question. Sorry.
How do you use that spot?
Oh, I just picked any spot. So if I like, if I do this, voltage is 0. 0, 0, 0. If I go like this, then I'm going around a resistor and it's sucking up energy. It's dropping off its voltage because it needs it to do whatever that resistor does, like if it's a toaster, a light bulb, or whatever. It's dumping energy right there to make that happen.
Honestly, it measures the change in voltage as it's going through.
It's like delta V.
And when you get to the end of the circuit, you no longer have any volts. So if you go from the end to the beginning, the difference is 0 instead of 6 volts.
You guys are awesome. Go ahead, Azulia.
What exactly do you mean by
The volts are being used up by whatever resistor, whatever appliance is attached. So if there's no place for the energy to be converted, it's usually converted into heat. Like, let's say this is a hot water heater, a dishwasher, and a PS4.
PS4?
Yeah, see, I got you there.
2 O's.
The wire, by comparison, isn't really sucking up energy. It's just delivering the energy. There's current running through it at all times, yeah. Yes. You got it, David. That is correct. Nami?
So basically, like, on the left side of the beginning, there's 6 volts, but once you get back to the right side of the ground, it's not.
Yeah, and then the delta would be 6. That's correct.
Oh.
Yes, that's the correct way to think of that.
But what's the delta?
Delta means the drop, or how much was available, or how much we used up. So you had 6 available, and then dropped 2, 4, 6, back to 0.
The delta is basically saying how much we can have.
Yes. I'm actually thrilled. I know this seems really simple, but if you get this, you'll be good to go for the rest of the week.
Yeah.
So that's to slow me down.
Okay.
All right.
Can I do that?
No.
Oh,
Go ahead,
we have to
Sarah.
do,
Here to here, what would that voltage drop be? 2. It's just like taking these wires and stretching them out a little bit. All right, let's see if you can do this. You ready? You with me?
Yeah.
Get, poke Nathan. Poke him hard. Poke him harder. No, there we go. That's better. All right.
Oh, I'm sorry, I broke the rule, guys, I'm sorry,
Okay. And then Nathan, I'm gonna give you a little break too.
okay.
Attaboy. All right, you ready? These fingers are a voltmeter. I know, you weren't doing anything wrong.
6. 2. 4.
Yeah, and I'm like, this is the inside.
2. 4. 6.
Why that say?
Because you're sandwiching the battery.
Yeah, whether it's this or this, either way it's 6, right?
Because
Okay, good.
0 one side.
Take a break, stand up, take a quick lap. You stand up.